Yes. All right, so this is going out to everybody here in the room and anybody catching up later. This is for you too, okay? By special request, backed by special demand, section 1.7. All right, infinite geometric sequences, that was Wednesday. Now, infinite geometric series. You've all taken sequences and series in the past. You know that a geometric series is a geometric sequence separated by addition symbols. All right? Now we have two things here. We have A symbolizing the first term, and R symbolizes the common ratio. What is a correct calculation for R? Well, you can take any term, Tn, and divide it by the previous term. The previous term subscript is n minus 1. So any term divided by the previous term. So you can take the second term and divide it by the first one, or the third one and divide it by the second one. It doesn't matter, any particular term. Okay, so this is called the common ratio. Or, in more layman's language, the number you're multiplying by every time. All right, so that's sort of a hands-on definition. All right, so we obviously have a geometric series right here. Yes, our first term is 4, and we're multiplying by 10 every time, so our value would be 10. Okay. We're hoping that you still recall your formulas that you've learned in previous math courses. The sum of n terms of any series, a r to the n minus 1, all over r minus 1. All right, so I'm going to just rewrite that over here because it's a little hard to read. All right, how many would say they've seen that formula before somewhere? Okay. All right, so this will add up all the terms right up to the nth term. So the sum from term 1 to Tn right there. Okay, now this only works if r is not equal to 1. If r, what you're multiplying by each time, is equal to 1, then of course we'll be dividing by 0 in the denominator there. So the formula becomes actually very, very simple if r is 1. The sum of n terms if r is 1 is simply n times the first term, na. So in other words, if you had an a value of 5, and your sum had 3 terms, 5 plus 5 plus 5, the sum would be 3 times 5. Very simple. Okay. Moving on. Oh, wait a minute. I missed something. But it won't let me. Oh, yeah, here it is. Okay. Infinite geometric series. Well, you knew it had to happen because calculus is, of course, a study that's really based on infinity. And we're not going to be just happy adding up n terms. That is actually so yesterday. We actually need the sum of an infinite number of terms. So what we need to do is we need to take this formula and adapt it for the limit as n goes to infinity. It's sure good we've studied how to do limits to infinity, because this will allow us to adapt this formula. All right, so what I'm going to do is I'm going to take this formula right here, limit as n goes to infinity of the given formula. Okay. I want you to recall something that we learned on Wednesday, last Wednesday. I'm going to put it up here. The limit of r to the n power as n goes to infinity is equal to 0 if r is less than 1. It's one of our limits that we studied on Wednesday. Let's put a box around it. That particular formula is going to be very valuable for us because that's exactly what we're doing here. We're limiting r to be between -1 and 1. That's the same as saying the absolute value of r is less than 1. In other words, r is tiny. So what's going to happen to our limit when r is tiny? Can anybody tell me what's going to happen to that term? It'll become 0. So what will be left? What will be left? Limit n approaches infinity, -a over r minus 1. We can rewrite that, of course, as limit as n approaches infinity of +a over 1 minus r. Simply multiply the top and bottom by -1. Okay, there's no n's left in that fraction. So therefore, the limit itself will go to a over 1 minus r, like that. Now, the limit as Sn goes to infinity is symbolized as S infinity. So a new formula was just born right here. That's exactly what we got when we worked it out step by step. We used a previous limit to show that r to the n would go to 0. Just like on our quiz, we had 3/5 to the n. It went to 0. So r to the n goes to 0. This term disappears from the limit. And we have -a over r minus 1, which is the same as +a over 1 minus r. It's normally written that way. It's normally written with the +a, not the -a. So we need to get used to it. So is this formula on your formula sheet? Maybe that's what you're asking. I don't know. Do they get a formula sheet? It might be on there. Some teachers do put it on there. Okay. So now, oh yes, it is on there. Okay. Does your notes have if and then a comma right there? Something's supposed to go in there. If absolute r is less than 1, the infinite sum exists. If r is greater than 1, less than 1, or equal to positive or -1, what happens to the infinite sum? It does not exist. That's a good question. That's probably what I would have written there. Okay. All right, so I'm going to erase this part because I just overlapped my boundary there. I want you to use the proper terminology here, the proper math terminology for an infinite sum that does exist. We say the series starts with a C, convergent. Ent or ant? It's ent. Converge ent. E-N-T. And of course, if this infinite sum does not exist, it's divergent. Yeah, did you hear like a water noise? Yeah. What's that? Oh, it's an email sound. All right. Okay. Whatever it was, I didn't mean it, okay? All right. Okay. All right, class, we're going to baby step our way through this. And on the first few examples, we're going to be content in finding finite sums. After we've done a few finite sums, we'll turn up the heat a little bit and do a few infinite sums. So at first, okay, what's the biggest room in the world? The biggest room in the world. Some would say the biggest room in the world is the room for improvement. Okay, you think it's cheesy, but still, there's some truth in it. So stay focused. Here we go. S6. All right. What would S6 be for this? A quick analysis shows that our first term is 4, and our R, common ratio, is, class, 1/2. Since this is a finite sum, and get this, the formula for finite sums is actually a bit more complicated than the one for infinite. Go figure on that one. Okay. Right, so this formula is a little bit more complicated. So S6 would simply be first term, 1/2 to the 6th power minus 1 all over 1/2 minus 1. All right, so all we do is simply substitute into this given formula. So we have a 4 for A, we have a 1/2, and we have an n of 6. I guess I could write that out there, n of 6. That's how many terms we want, right? Okay, so you know what would be really fun? Working this out without a calculator. Let's do it. Yeah, that'd be cool. All right, so 4. All right, so 1/2 to the 6th power. I'm going to say that's 1/64. Minus 1. I'm going to say that's 64/64. And 1/2 minus 1, I'm going to say that's -1/2. 4 divided by -1/2 would be -8. And 1 minus 64, -63 over 64. And we're lucky because the 8 and the 64 divide out. So our answer is 63 over 8. Oh, that just revitalized my brain cells doing that. I feel smarter already. Okay, I'll just review, okay? Sorry. You can always get it on your calculator, okay? 1/2 to the 6th power. 2 to the 6th power is 64, isn't it? 1 can be written as 64 over 64. 1 minus 64 is -63 over 64. 4 divided by -1/2 is -8. And then the negatives cancel. And 8 divides into 64 8 times, so you get a denominator of 8. But if you didn't like all that, you can do it on your calculator. Okay. All right. Let's try S5. Okay, now class, maybe you felt a little bit left out. Okay, so I'm going to give you one to do. All right, example 2. Okay, your chance to kick some math butt. All right, here we go. Example 2, much like example 1. How about you try it? You don't have to do it in your head, though, if you don't want to. You can do the calculation on your calculator if you wish. All right? I was just sort of fooling around there. you're not sure what to do, you can watch me work this out on the board. Okay, so make sure your substitution is correct. Take a look at what I put on there. Once you start working this out in your head, it gets a little addicting. So now I can't quit. So -2 to the 5th power is actually -32. -1 is, whoops, getting too excited. -32 minus 1 is -33. And when I do that and multiply it out, I get -22. Did anyone get -22? Okay. Example 3, I promise you, is going to be the easiest example you get today. What if our sequence was 5, 5, 5, 5, 5? A is 1, 5. R is 1. When we have an R of 1, our S10 would simply be 10 times 5, or 50. Wasn't that fun? Okay. That's okay. That's okay. All right. Okay. There are 2 parts to example 4. The first part is where we state whether it's going to be convergent or divergent. That's the first part. The second part, if it is divergent, if it is convergent, we need to find the sum, right? So if it is convergent, we need to find the sum. It's quite simple, class. Just look at your R value. Your R value holds the key to convergence or divergence. The question you need to ask yourself is this: is my R value absolute value less than 1? And the answer is yes. 1/2 is obviously less than 1. All right? So this one will be convergent. Therefore, I can use my new formula, S A over 1 minus R, to find my infinite sum. Let's put the sum infinity right there. So S of infinity will be A value over 1 minus the R value. Could you work that out for me? What is 4 divided by 1 over 1 minus a half? 8. By the way, I hope you can see that this formula saves you a lot of work, because the only other way to do this would be to take 4 plus 2 plus 1 plus half and keep going for quite a while and look and see what you're approaching. Right? This is much more streamlined. What is your comment about B? What can you say about question B? Divergent. We have an R value of -2. Obviously, the absolute value of -2 is 2. It's way too large. This R value is too large for convergent, so divergent. Therefore, there will be no sum available for this one. Now, when our R value is 1, we're right on the borderline. We're right on the borderline, right? Our R value is 1. Unfortunately, we cannot accept this. And there's no sum available. And I know what you're thinking. You're thinking, Mr. Ashton, there is a sum. All I have to do is go 5 plus 5 plus 5. Oh yeah, but where would you stop? Remember, this is infinity. We're going to infinity here. Eventually, you'll run out of time and you'll give up. So there is no sum available. If you only had 100 terms, yeah, you'll have a sum. If you have an infinite number of terms, you will not have a sum. Okay. How many of you are familiar with sigma notation? You've seen it before. Okay. It does mean sum. Perhaps I'll do an easy example first. Maybe you can find it at the bottom of the page. Let's call it example F. Let's start with a finite sigma before we do anything else. So in question F, I'm going to go from n equals 1 to n equals 3. How do you do that? First of all, substitute in 1. Then put a plus sign. Then go to 2. Put a plus sign. Then go to 3 and put a stop or stop there. So sigma tells us where to start and where to stop. Maybe when you were a younger kid, you played Simon Says. Well, this is Sigma Says. Sigma says start at 1 and end at 3. Start at 1, end at 3. It's instructions, people. It tells us exactly where to start and where to stop. So this is a finite sum. And this gives us what's called the general term. That's what you're substituting into each time. So substitute in a 1, then a 2, then a 3, and stop. That's what it means. And of course, this is a trivial example. The answer is 14. Let's go to infinite sigmas now. If we don't want to stop anywhere, we put the infinity symbol on top of the sigma. That means this is an infinite sum. But we will be starting the same way. We'll be starting with 4 times 2/3 to the 1 minus 1. Then we'll go to 4 2/3 to the 2 minus 1. Then we'll go to 4 2/3 to the 3 minus 1, and so on. The way and so on is written correctly mathematically is with 3 dots. Not 2, not 4, 3. So just go plus, dot, dot, dot. So we have to make sure we see our pattern here. All right, so what we get here is 4 times 2/3 to the 0, which is 1. So 4 times 1. Here we'll have 4 times 2/3, which is 8/3. Here we'll have 4 times 2 squared over 3. 2 squared is 4, 16/3. Now we're hoping, sorry, these are wrong. Thank you. 16 ninths. Let's put that down there. Okay. Now you're supposed to be able to look at that and see what your A value is and what your R value is. If you can get A and you can get R, you can get the sum to infinity, can't you? All right, so you have the power. So go ahead in question D and write out the A value, write out the R value, and then work out the sum to infinity. Oh, maybe I shouldn't assume that. Maybe I shouldn't assume you can get a sum to infinity. All right, so I'm hoping for this one. Because your R value is less than 1, we will have a sum to infinity, won't we? So the sum to infinity will be the A value over 1 minus the R value. So 4 divided by 1 over 2/3. Can anybody give me an answer for that? What is the answer for S infinity here? What does this work out to? 12. All right, so 4 over 1 minus 2/3 is 12. Class, if that was a little puzzling for you, don't worry, we have another one. Question E is very similar. I'm just going to erase this one because it's pretty straightforward anyway. Okay, question E. Let's write out the first few terms. All right, so we're starting with x equals 1. So we're going to have 1/2 squared, 1/2 to the 4th power, 1/2 to the 8th power, and so on. Simplifying our terms, 1/4, 1/16, sorry, was that 8th power? Yeah, 6th power, sorry. Mistake again. Making mistakes today. Stupid mistakes. All right, so 1/16, 1/64, ... Okay. Could you write out your A and R values now? What are your A and R values for this infinite series? A is 1/4. And as luck would have it, R is also 1/4. They're both 1/4. So what's the sum to infinity? The sum to infinity will be the A value over 1 minus the R value. 1/4 over 3/4. 1/4 times 4/3. And the 4's do cancel out. So believe it or not, this one actually goes to a limit of 1/3, which is strange because there isn't any 3's in it anywhere. But if you took your calculator right now and did 1/4 plus 1/16 plus 1/64 and so on, you'll get closer and closer to 0.3333. All right? All right, people. We've got to make it through one more page. All right. Sometimes you will get sort of a hybrid sequence, a sequence that's only partially geometric, such as in the case here in example 5. In example 5, the first two terms do not fit the geometric pattern of the other terms. Did you notice? 10 and 4 don't have anywhere near the same ratio as 1 and 3. However, the next term here is 1/3, which does continue the ratio. So it looks like we're good from here on in. It looks like these two terms are the oddballs. So 10 and 4 don't fit the other pattern of the other three. Now keep in mind that this is still a sum to infinity. So when it's written this way, you got to hear this part. With the dots right here, when it's written this way, you assume it's this pattern only that's being continued. Right? Okay. So the 10 and the 4 have to be done separately, but that's easy. 10 plus 4 is 14. So what we need is 14 plus s infinity. 14 plus s infinity will give us everything that we want here. In order to get the s infinity part, though, I need an a value and I need an r value. I'm going to write something in now. I'm going to write it in purple, even though I'm holding a green pen. And yes, it's a secret agent pen. All right, so 3, 1. Now, I wrote that down, but is it right or not? You can vote in just a few seconds. If you think it's right, could you raise your hand now? Okay. How many think it's incorrect? Okay. The first term where the pattern starts is 3. So A is definitely 3. And if I divide 1 by 3, I get my R ratio. It's 1/3. So this is definitely correct. So I have two parts. I have the 14 from the 10 and the 4, and then this part. So I would subtract the 1/3 from the 1, and I get 2/3. How are your fraction skills? They will be tested in this unit. I hope that everyone here can see that when you take 1 and subtract 1/3, you get 2/3. If you didn't see that, then maybe it would help if you write 1 as 3/3, right? 1 is the same as 3/3. Take away 1/3 is 2/3. So what's 3 divided by 2/3? It's the same as 3 multiplied by the reciprocal, right? So what's 3 times 3/2? 9 halves. 9 halves is, of course, the same as 4.5. So we have a total of 18.5 here. Or 37.5. I mean, 37 over 2. Okay, now, in example 6, now we're turning things around on you. We're saying find the value of x, or the values of x, that will make the series converge. All right, so let's find values of x that make this series converge. I hope you can see that our a value is 3, and our r value expressed in algebra would be what? What's our r value in example 6? What's an algebraic expression? X minus 4. That's what you're multiplying by each time. So you started with 3, then you multiplied by x minus 4, then you did it again. it's obviously the R value must be x minus 4. What must be true about this R value to get convergence? The R value, the absolute value of the R value must be less than 1. That means the absolute value of x minus 4 must be less than 1. And right now you're thinking, it's sure good we studied those things in grade 11. I'm sure you did. You guys took 20-1, right? I'm thinking you did. Okay. I'll show you a quick and easy way of solving these ones, okay? Absolute value being less than a number can be expressed like this. That's really what it means. It means your x minus 4 is in between -1 and +1. This statement, to a trained mathematician, this statement means that statement, and vice versa. If your absolute value is less than 1, that means you're between -1 and 1. These are equivalent statements. Now let's take this equivalent statement and add 4 to all 3 sides of the inequality. If we add 4 here, and add 4 here, and add 4 here, what do we get? Yes. Exactly. So an inequality is a delicate balance, just like an equation. And when you have 2 inequalities in the same statement, you can add things to all 3 parts and still have the equivalent inequality. So I added 4 here, here, and here, thus isolating my x. So if you have x less than 4 in between these two, it means your x was in between those two. Okay? This is actually now the condition for this series to converge. That's my condition. Now, unfortunately, that's not the only thing we're supposed to do. We're supposed to find this condition, which we've done, but now we must find an expression for the sum. I just have one minor complaint about your workbook, whoever wrote it. It's really good. I like the examples in it. There just isn't enough space. So now, what am I going to do? And this is being recorded. Sorry, everybody that's listening. This is recorded, but I'm running out of space here. Okay, so I'm going to just pretend you guys have all that down. All right. So I'm now going to do the actual infinite sum, this one right here, using the information I have. Okay? Algebraically. So what will it weigh? It'll be S infinity equals the A value over 1 minus the R value. And the R value is a binomial. Every good binomial deserves a pair of brackets. All right, so it's 1 minus brackets x minus 4. Could we simplify the denominator? What would it be? 3 over 5 minus x would be the simplified expression. 1 minus x minus -4 turns the 4 positive, and that positive 4 combined with your positive 1 gives you a positive 5. Are you on board? You're on board? Okay. So that's an algebraic sum there. So if you did have an x, remember this was your condition. If you did have an x that was in this range, you will get a sum, and that's how you find it. If your x isn't in that domain, forget it. You're not going to get a sum. Don't even try. Okay, now we're going to go back to junior high school. Yes, example 7 is going to take you back there. Grade 9, where you were working on repeating decimals and how they had fraction equivalents. We're going to take a look at this again, but from a Math 31 point of view. Okay, we're going to start with the repeating decimal 0.23. How do we change it to a fraction? Believe it or not, we can use infinite series to help us with this. Yeah, I can make an infinite series out of this. First thing I write down that it's equal to 0.23. Well, it's not quite equal to 0.23, is it? But what if I did this? Am I getting closer? Oh yeah, I'm getting closer. This is now 0.2323. Guess what my next term would look like? Yeah. Sort of cool, right? Put a plus sign and 3 dots. We're in business. We have just turned a repeating decimal into an infinite sum. This is exciting. Yes. Well, we wouldn't throw a party or anything, but here it is. By the way, if you were doing a question on a test and it had 5 parts, and you did part A, and you did part B, and you did part C, and you even did part D, what time would it be? No, part E time. It had 5 parts. Okay. Sorry, that was bad. Would you believe I made that up myself? Okay, yeah, I did. All right. Okay. It might be pretty obvious what your A is. Maybe it's not quite so obvious what R is. Thank you. Did you all hear what he said? Yeah, like what he said. All right, so 0.01. That's your R value here. Guess what? The infinite series formula is just waiting for you now. Give me some math action here and work out what fraction 0.2323 repeated is as a fraction. Let's get it now. All right, so I'm skipping a step and I shouldn't. And of course, a quick calculation on your calculator will confirm that 23 over 99, if you just go 23 over 99, you'll get the 0.2323 thing. They only give you one of these, eh? Let's do another one. They're groaning. I'm giving them an example 8 for free. I'm not even going to accept any tips today, okay? Some of you guys left tips behind on Wednesday. It's okay. You don't have to do that. I'm a teacher. All right? I'm not a server at a restaurant. Okay? All right. Here I go. I'm going to get you a harder one. suppose I wanted to change 0.9 repeated to a fraction. What would it be? Write it out. First term would be 0.9. Second term, 0.09. Third term, 0.009. So it looks like we have an A of 0.9 and an R of 0.1. 0.1. So our S infinity formula would be 0.9 over 1 minus 0.1, 0.9 over 0.9, 1. So we just have a nice little mathematical proof that 0.9 repeated is actually the same as 1. And you can also prove that 1.9 repeated is the same as 2. Can you imagine how impressed your parents would have been had you counted to 10 as a little kid using the 0.9 repeating? That would have been, yeah, okay. All right. Oh, that one was sort of a silly example, so. I just want to make sure you guys are getting this, okay? So in example 9, I want this guy changed to a fraction, okay? Change that guy. 1.267. The bar is across the 2, 6, and the 7, but not across the 1. Whoops. I'm going to just give you a little hint on this. Separate out the 1 because it's not part of the repeating pattern. And so on. So you can try a few of these. They're like fun to do. And page 57. Page 57 is your assignment. This is questions 1, 2. Oh. So there's no comma between 2 and 3, so that means that it's 2 ACE and 3 ACE, I think. And then number 4. Is there a 2 ACE? I don't know. Might be a comma there. I'm not sure. Yeah. Okay, you can go to the back. Oh, sorry, that's on the tape. Sorry. Just a second.